Now consider the same thing on the right. We have minus of UR. The minus sign is because on the right side, the negative normal minus n is actually negative, right? So we have minus UR times rho UR times dy dz. And then we also have the upper side and lower side. On the lower side, minus n dot with v gives us the y directional velocity. So we have v at the bottom times rho u, right? So because we are considering this, we're just copying the u here. ub times dx dz, and minus v at the top times rho u at the top dx dz. So that is the four terms corresponding to the four sides of this this rectangle constitutes the influx of x momentum. And you may be asking, how about the influx in the z directions? It's actually zero, because we are assuming everything doesn't change in the z direction, right? So if there is any influx of momentum through the z direction, the same flux is going out towards the other side. So the z direction we don't have to consider. So this whole thing is the influx of momentum. And then we have to add with the pressure force. So that's basically pressure on the left times dx dz, not dx dz, dy dz. Right, dy dz is the area on the left, minus pr times dy dz. So now that's the entirety of this momentum conservation equation. First thing you see is that there are some nice things we can cancel out, particularly delta z, right? Delta z appears in every single term. So that's the nice thing about a two-dimensional flow field is whatever the length of the z domain you have, it doesn't matter to the equation. Everything cancels out. So let's carry this over and also divide everything by dx dy, so that this thing gets canceled out. We just have a time derivative of the momentum density. And if we divide this by dx times dy, the dy goes out and we have a dx. Dy goes out, we have a dx. Dx goes out, we have a dy. Okay, and the dy gets canceled and we have a divide by dx. So let's write this down in the next page to see what we get. ddt of rho u, okay, is now equal to, let's look at the first term. It is basically the ddx of rho u squared, right? Except it's negative because it's the left minus the right. If we have right minus the left divided by dx, we get the derivative. Here we get the negative of the derivative. So, okay, so here let's actually replace this total derivative by partial derivative, because instead of looking at a total quantity, we are now introducing derivative in all directions, right? We're introducing derivative in t, in x, and in y. So here we have a derivative of rho u squared in the x direction. And the second line that's divided by dy really is pretty much the same, but we have a rho times u times v, right? We have a v term and a u term that's multiplied together, divided by dy. Okay, finally, the pressure force, again, it's a negative of dp dx. So that is the differential form of momentum conservation in x direction. We can similarly write the momentum conservation in the y direction. What we get if you do the same derivation, we get a time derivative of the momentum density in the y direction. That is going to be equal to the derivative of rho v square, but in the y direction, and minus the same derivative with u and in v, but taking derivative in the x direction. And then we have minus the derivative of pressure in the y direction. So these two constitutes the momentum conservation equation. Specifically, if you combine these two, if you look at these two equations as the two components of a vector equation, you can write it in the vector form of d dt of rho vector v, right? Where consider this vector v just as a u and v, the two components of velocity. That can be written as a pretty interesting form, right? So first of all, you have to combine these the x derivatives and also combine these y derivatives. If you combine the x derivatives, what you get is a partial derivative of x. Look at the common terms. The common terms are rho, right? Both has a rho, both has a u, okay? But one has a two u's, has a u squared, the other has a v. So it's rho u times the vector v. Of course, we have a negative. And then look at all the terms that has a derivative of y. We have d dy. Again, there is a common rho, there is a common v. And then the first equation has a u, the second equation has a v. Therefore, we have this vector v. Right? All of these derivatives are, all of these are inside the derivative. And then minus, now here's the interesting part. In the first equation, we have a derivative with respect to x. The second part, we have a derivative with respect to y. And that means we have this gradient of pressure inside this equation. That's where the negative of the gradient of pressure comes from, right? So through momentum conservation, we derive that the force density, the unit amount of force, the amount of force per unit volume is the negative of the gradient of pressure. So this is the vector form of the momentum conservation equation.